In exoskeletons and wearable robots, tightening straps improves force transmission but can cause discomfort, while loosening them improves comfort but reduces transmitted forces. Previous work studied how strapping pressure relates to comfort, stiffness, and energy dissipation during arm sliding. However, only end-effector measurements were considered, leaving the internal cuff interaction unmeasured, and strap pretension was kept constant, overlooking the risk of skin injury from sustained pressure. In this paper, we propose a cuff instrumented with 12 triaxial magnetic force sensors and 3 inflatable straps whose pressure can be controlled in real time. The cuff is mounted on the end effector of a 6-degree of freedom robot, which is also equipped with a 6-axis force-torque sensor. This setup allows us to measure normal and shear forces inside the interface and to adjust strapping pressure to study the spatiotemporal behavior of the attachment during wearable-robot interactions. The cuff is driven in repeatable oscillatory motion relative to the arm. 3 inflatable straps, each set to low, medium, or high pressure, produce 27 configurations, each tested on 20 participants for 30 seconds. Configurations are grouped by total pressure sum for statistical analysis. We collect comfort ratings, relative motion from Vicon markers, and forces from both the end effector load cell and embedded cuff sensors. End-effector analysis using a mass spring damper model shows that configurations with equal total pressure yield statistically equivalent stiffness and damping, while differences emerge across pressure sum categories. This suggests that multiple pressure distributions can achieve equivalent force transmission. Inside the cuff, quasi-stiffness computed directly from cuff sensors decreases with pressure, but after linearly fitting cuff forces to end-effector forces, R squared equals 66.9%, the trend reverses, matching end-effector behavior. Similarly, end-effector energy dissipation increases with pressure, while cuff sensor dissipation decreases by up to 64% across categories. We also test a dynamic redistribution condition, where the total pressure sum is fixed at 6 but redistributed across straps based on cuff position. The dynamic redistribution condition achieves statistically equivalent stiffness and damping to static configurations at the same pressure sum, while reaching comfort levels comparable to lower, more comfortable pressures. This indicates that dynamic strapping can maintain force transmission while improving comfort. These findings are relevant for rehabilitation applications. For example, assisting users with motor impairments, where a robot could automatically don the device, apply an appropriate pressure distribution, and then adapt strap pressures dynamically during movement to maintain effective force transmission while minimizing discomfort.